I wanted to say a few words about the second homework assignment. Some people came with good questions into the office, and I realized it's probably more confusing or more intricate than people think. So let's say that I have these two, what was it, quiz and it was question and choice, right? That's not right. So I have a class question. I have a class choice. And they're specified in the homework assignment. So we say class question, subclass CSV base, and then we have a help me out here. Has many? I don't remember. Has many choice, and belongs to answer class name. Head. So, how many methods does question have?
I thought the two methods has underscore many and belongs underscore to are the methods which are defined in CSV base class.
Okay. So let's ask how many methods does this one have?
So it has underscore many, belongs underscore to,
Yep.
and self dot inherited class.
Okay. So well, I'll come to that in a minute. So we have these two methods, has many, belongs to.
And find ID and
Exactly. And then these two find ID and find each. Right. So these are methods of the superclass that you inherit. And now these are class methods, right? These are not instance methods, they're class methods.
So we do have one question, sir.
Yes?
So when are they exactly using the self keyword for methods?
When you want to define what a Java would be a static method.
Right. So you don't have to have instances for that. To call those
Right,
methods.
right. And in fact, there are yeah. I guess that's just like a Java. That's like a static method in Java, or in Scala, like an object.
Right. So these methods have to be static.
Yes.
Self.
Yes, they're all that define oneself. That's how you make a static method in Ruby.
So is it necessary that even find ID and find it should be static?
Yes, because by the time that when you want to find an object, let's say you want to find question number 3, you don't have a question yet.
Right.
So it has to be static. So it has to be a static method. When you say find by ID, find ID,
Find ID.
3, you don't have the question object yet.
So basically you're finding the question and then you're assigning it to your object.
Then you're making a new object.
You're making a new.
Yes. So if you call question dot find ID 3, and now you assign that to Q, then Q is now an object of that question. So it's the job of find ID to make that object.
So find, when I say question dot find ID, I get the third question
Yes.
into my Q object.
Yes.
What exactly happens when I call? Now, when I say question dot find ID, it has nothing to do with the choice class.
Oh, it does. It does, because what object do we expect? The object, let me put that on a new sheet here. Just stupid as that. So here's my question object. It has a text. It has a, what else does it have?
Question ID.
It has an ID.
And answer ID.
It does not have an answer ID.
Choice ID.
It does not.
It has answer ID.
It has an answer. Because the belongs to says that you actually need to produce the answer. So it has an actual object. I guess uppercase A. That's how it was. And it also has.
Oh, so the belongs to stores the foreign key, which means it's actually has the object.
It has to translate the foreign key into the actual object. That's what an object relational mapper does.
So basically, using the answer ID here, we go to the choice class
That's
and
correct.
get the corresponding thing, and
Yes.
we also include that in the question object.
That is correct. Yes. So this thing is going to be a reference to a choice object, and you are absolutely right that what must happen during find ID is that it must make that lookup in the choice table. So it must open the choice.csv, look for the thing.
So it gives.
But actually, you know what it can do? It can recursively call find ID for the choice.
It cannot.
Yeah, it can. And it should. Since you're already implementing, you might as well use it. So in my implementation, that's exactly what I do. Is I call find ID again, but this time on choice, of course, and with whatever ID I found there. That gives me some object back, and then that's what the stuff is. So just as a tip.
So it just gives the a record from choice which corresponds to the correct answer.
Yes?
And what is find underscore each doing? It gives all the options.
No, find each, it invokes a block on each of them. It's like for each in Scala. So it just, if you wanted them all back, you would have to put them in an array. Yeah?
So, and coming back to the previous question.
Yes?
When you are actually calling find the ID on choice.
Yes?
So you make an answer object at that time when you call it? Because what
I make a choice object.
Make a choice object.
Yes.
So
Just by the, it'll do the same thing. It's a recursive call.
so that would mean answer is child of choice.
No, it's not that simple. You can't think of, because you can have relationships going back and forth, so you can't think of one thing as being parent or the other thing as being child. Let me come to that.
So how can you return a choice object to answer?
Well, the code for it is going to construct a new object by calling initialize.
Right.
It's going to set all the fields,
Right.
and then it's going to do whatever it must do with choice might also have relations. So it'll do whatever it must do with the relations. And when it's done, it gives it back. That's what find ID does. It reads the record itself, and fills the simple slots, the straightforward properties with what it finds in there. And truth be told, I think in my solution, I do put in a field for the answer ID as well, because it was easier to put it in than it was to suppress it. But I do actually look up the answer then, because that's one of the relations. So for each of the relations, I then do whatever the extra step is required by the relations. There are two kinds of relations that belongs to, and need to call find ID again. The other relationship, the has many, I have to work even harder. I have to make an array, because that's the only collection that I know in Ruby. So that's 4 choices, right? So I make an array, and then I have to read in the various choices. And I think I'm using the for each for this just because it's there. But maybe I code it up by hand, I don't know. So you can be as inefficient as you like. You can open the file again, you look through all of them where the foreign key matches, and then you put it. Yeah.
So my question is, all this process is happening inside find ID method. First,
Yes.
I'm calling the find
Yes,
ID
that's
question,
correct.
right? So what exactly is happening inside the has underscore menu method? What are we
Okay.
doing inside?
Okay, that's a good question. So they have to put in enough data into the object that find ID can do its job.
Right. So that was my question, because when initially CSV base reads
Yeah.
the CSV files, it just has ID, text, and answer ID. So now we
Right.
also need to have answer and choices.
Yes, and so you certainly would want to make those fields, but I think you need to do a bit more than that. You also need to keep a little, you might have more than one belongs to.
Right.
And each belongs to could also have properties. And so you need to store those, so that when you process the belongs to, so you can iterate through all of them and process them in find ID. So the job of initialize is to put into the object whatever find ID will need when it is later called. You will also need to remember all of the various has many relations, so that you can process them later. So you will need to put in some data structure, and the only data structures that you know are arrays and maps. And so that's what I used to put in. So maybe an array of the has many relationships, and I put in maybe a map of the, because there was you could have class names that you also needed to somehow store. So I put in some ad hoc data structure for whatever it is that was needed later. So the job of the initialize is merely to prepare the object for a later call to find.
The job of initialize or job of has many?
Oh no, I'm so sorry, has many. Yes, has many.
And what if in belongs to you have optional parameter class name?
Right. And that was, if you look at the answer, I want to call the field answer. I didn't just want to call it choice, because to the programmer, it makes sense that it is an answer. But the type of it was choice. And I had to have some way of specifying that. I took that straight from Active Record. This is not my own invention. This is the exact same convention that they use for this relationship.
So if answer is a choice object, will it have all the fields that choice had?
All choice objects have all the fields that choice has. Yes.
So in my question will I have just one field saying answer, or
Yes.
will I have?
No, you will have one field saying answer that has a reference to the choice
Which is
object.
actually an array, probably any.
No, it's just a reference. It's a single value
Okay, it returns an object.
that has a reference to an
So when
object.
I say some question of dot answer, it returns an object.
Right, exactly. So you could say q dot answer dot text. Absolutely. Okay, now there's one remaining complexity, and that is when you look at the choices, there might be 4 choices. One of them is the answer, and you need to set the reference
Back to itself.
so that it points to the right one, because otherwise you would have 2 copies of that object, and that's not what a programmer would expect. Right? A programmer would say, well, they're the same thing, so they need to be expressed with the same reference. Yeah?
Can you extend it really?
I don't know. So how do you do that?
Section.
How do you make that? How do you get them to the same reference? Now, this is a problem that every OR mapper has, right? It's not something that I just came up with. So how do they do this? Let's first of all see where it comes up. So at some point, we're going to be saying, we're reading in choice number 15. And then someone must realize that we have already seen choice number 15. And then instead of constructing a new object, we need to get a reference to the existing object.
So for that we have to check all the existing objects of the class.
Right.
So that's got something to do with object space.
Yeah, or you could just call it a cache. So you have to cache all known objects. And so what find ID actually does is, before it goes out and opens a file and looks for the record, it first looks in the cache to see whether it already knows this particular object. So in the cache, you have to have it organized by the name of the class and by the primary key. And if it has already seen choice number 15, then it simply returns what it has for choice number 15. And then it doesn't have to go and read it. If, on the other hand, it has not yet seen it, then it needs to go out and read it, and it needs to also remember it. So that next time it returns a reference to the same thing. Any more questions about this? All right. So go on to the lecture then. Yeah. All right. So we're going to be looking at scheme, and for a couple of reasons. One is that there's a whole bunch of really interesting languages that are derived from good old Lisp, such as Clojure, that's getting a bunch of good buzz right now. And all of those languages have this very interesting syntactical structure that they have lots and lots of parentheses. And there are many programmers who refuse to look at one of them because they dislike the parentheses. So for about 3 weeks or so, we're going to be swimming in a sea of parentheses. And after that, hopefully everyone will have said, well, the parentheses are the least of my problem. And thereby have internalized that they actually have some real advantages. So yes, there will be a pain for a few days, but eventually they become kind of second nature, and then you never have to worry about it again. And that's where you kind of want to be. The other one is Scheme has for over 50 years given us more metaprogramming than Ruby could ever hope for. Because in Ruby, what you can do is you can manipulate the object model, and that's nice. But in Scheme, you can manipulate all your code. Every bit of code that you write can be changed by Scheme itself. So it doesn't get more meta than that. And many people put that to great advantage. And finally, we're going to be talking about continuations. And if you've never seen continuations, you probably think that you know everything that there is to know about control flow. Because what's control flow? There's if and while and for. But continuations are this advanced control flow construct that is incredibly powerful, that lets you go back in time and forward in time and do all sorts of interesting things. And so we'll go through that and see how it can be useful for writing all sorts of applications. All right, so in Scheme, everything is a list. Absolutely everything that you see in Scheme has the form opening parenthesis, some kind of an operator, argument, and a closing parenthesis. You have just learned everything there is to know about the Scheme syntax. This is it. So actually, there are people who use Scheme as the first programming language, like for freshmen or even in high schools. And because you can show them, when you add two numbers, the operator is plus, the arguments are 3 and 4. So you put the parentheses, operator, arguments, and then it computes the answer, which is 7. You have more summands, you put them all into a longer list, and it adds them all up. You want to multiply, and then add. So over here we compute. Oops, the comment is wrong. We add 4 and 5. We multiply the whole thing by 3.
The separator over here in the space?
Yes.
That's it?
Yes. Yes, there are no commas. So, and there's no operator precedence. There's no notion that plus might be stronger or weaker, because there's no need for it. There's nothing in the syntax that would let you do anything with preference. So here's an if statement. It starts with if, condition, true part, false part. That's it. Couldn't be simpler, right? That's what an if statement is. It has 3 parts: the condition, the true part, the false part. Here they are. Yeah.
Yeah, if I write like star 3, 4, and then after that I just write plus 3 or 5.
Okay, that's a good question. So he wants to write star 3, 4 plus 5.
Yeah.
And so now the multiplication operator sees 4 arguments. It sees 3, 4 plus. So it would not know what to do with the plus sign.
Is it like, isn't it something like left to right operator precedence? Or
There is no operator precedence because this is your operator. This is not an operator, it's an argument. So, in fact, you can figure out exactly what the star function here receives. It receives a number. What's this?
Number. It should be an
Operator.
It's the plus function. It is the addition function. And it receives another number.
So can we?
So this thing is always a function. This thing must be a function. And this thing can be anything.
Like if you put 7 parentheses inside of
what was going on here. You see this plus 4, 5 gets evaluated to 9.
Yeah.
And then it gets multiplied with that. So the evaluation is that when you see a list, you evaluate it by applying the first thing to all the others. That's the one and only evaluation rule. Everything else evaluates to itself. So in this case here, if you would have this to write plus, for example, that's a perfectly valid scheme program. And it simply returns the addition function. So to define your own functions, you use the keyword define. Define takes two parameters. One of them is a list consisting of two names, namely the name of the function and the name of the argument. And then it contains a statement, and that's the code of the function. And then once you've defined it, you can call it. Now, what if you actually want to use a list as a list? So over here, I want to have the list 1, 2, 3. Then you have to put a quote in front of it, because what would happen without the quote? It'll evaluate 1 and say, well, that's not a function. And the thing has to be a function. So the quote stops some things from being evaluated.
Is it like an escape character or something?
Not really. I mean, I guess you could be metaphysical about what exactly that is. It means it's a quote. It means don't evaluate this.
Maybe like put it out of the parentheses, as in just code 1, 2, 3.
Oh, you can't do that. So because a program is just one item. So this would be a valid program, but there's no room for anything else.
What was the fourth line again? Number 17?
Oh, that's true.
Yeah, well, with 2, 3, or 4, like what is that?
Oh, it means that's the condition. That's the positive branch. That's the negative branch. So in this case, because true is true, it picks the positive one. Over here, you see it again in the factorial. If it is true that x is less equal 1, then it's 1. Otherwise, it's the product of x and the factorial of x reduced by 1. And here you see this phenomenon of all of the parentheses function. The editing environment helps you keep them matched. So the syntax is so simple that you can teach this to a 9th grader and they will get the syntax within one lecture. And that is the reason why Scheme has failed as an instructional language. Because when you teach someone Java, it takes them several weeks of figuring out how the IDE works and how one deals with syntax errors and semicolons and quotes and all of that stuff. And in those several weeks, it's past the drop deadline. Whereas in Scheme, you get to the point where people actually have to start thinking about the programs and not about the syntax and the IDE in the second day of class, and people decide to drop. So, and that is the actual truth. People have had that kind of experience whenever they offer these courses. That it just gets you to the moment of truth so fast, it's not even funny. All right. So it's dynamically typed, just like Ruby is. You can put anything in a variable that you want. Here we're putting it 1 into x, and then later I can put a list into x. It's functional, just like all the languages that we've been looking at. So it has the same old map construct that you've seen from Scala. Map takes a function. Here, the function here is the squaring function. So for historical reasons, one uses the keyword lambda, or here I'm just using the Greek letter lambda, so I don't have to write out lambda. And whenever you see that thing, you should think function. So for some reason, some mathematician 80 years ago decided to write the functions with using the Greek letter lambda, which was a totally random choice. There was no particular reason. and the programming languages have picked that up, and we just have to get used to it. So when you see this funny simple thing, function, it's a function consuming an x and yielding the product of x and x. So this is the squaring function. So we're mapping the squaring function onto the list 1, 2, 3. Notice that the list is quoted because I don't want to evaluate it. I don't want 1 to apply to 2 and 3. And then the result of that is the list of all of the answers, in this case 1, 4, 9. It's exactly the same map that you've seen in Scala and in, or like, there's a for each thingy in Ruby whose name I can't remember. All right, so control flow, you have if, you have and or. You have a conditional branch expression that's kind of convenient maybe, where you have multiple conditions. So here, if x is less than 0, then you yield -1. If x is equal to 0, you yield 0, and otherwise you yield 1. And because there's so many parentheses here, it's common to, you're allowed to switch between the round and the square parentheses, the square brackets. And so it's kind of common to use the square ones for the pairs to make them a little easier to read. So this is kind of, like a cascaded if statement, or you could think of it like a switch or a match statement. I don't know if there is a while. We'll never use it. So if we ever wanted to do some looping, we'll do it with recursion or by mapping over a list. The one thing that we often need is when you have local variables, it's a little cumbersome to do. You have to use this let construct. Let has a list of variable definitions, where each of them is again a 2-element list consisting of the variable name and the initial value for it. And the initial value is pretty much the final value because we're not really learning how to mutate anything. I think that's going to be true. After the let, then you put whatever things you want to have happen, 1 or 2 more expressions. Again, because we don't really have mutation, it's almost all the time just one expression. So you can think of this thing as kind of being like a block of a body of a function where you define your local variables and then you do stuff inside. And the let, I guess because it's like mathematical, where you say let x equals 0 and y equals 1 in this expression. So we've already seen an anonymous function. And so here's another example of one. This one takes 2 parameters, x and y. Then it adds them up. It multiplies the thing with 0.5, so it takes the average of x and y. So this is an anonymous version of the average function. You can actually write the lambda if your keyboard has a lambda key. With some operating systems, it's very easy to make a lambda key. Like my keyboard, I can type lambda by typing caps lock GL, and I get lambda. But that doesn't work on all operating systems. In fact, I don't know how to do it anywhere but on Linux. But you can just type lambda like this. And in Racket, I think you can do control \\. So it's exactly like in Ruby, just the syntax is a little different. In Ruby, I would have written this function as vertical bar x, y, and then 0.5 times x plus y. So if you look at these two, you see that the syntax is different, but the basic meaning is the same. In Scala, I would have had to put in the types, and otherwise it would have looked well. I guess that lambda there is kind of characteristic. In JavaScript, lambda is sensibly called function, and so this almost looks like looks very much similar. So and you always want to do this when you want to pass some functionality to some other function, like here the map function. You can define various things. You can define a variable by using the form of define where the second slot is not a list, and then it just defines a variable like a global variable. You can define a function like this. Now, it's actually never really necessary to use define, because you could also say, like I have here, you can use let and then set x equal 1 like this, or you can let square be this lambda. So define is just, it's just there to make things look a little bit easier to read. but lots of people use define quite rarely. Lists are, if you use like C++ lists or Java lists, these lists are very, very different. In C++ or in Java, to access a list, you use an iterator, or you kind of point to the first node, and then to the next one, and then to the next one. And here, it's much, much simpler. You deal with lists by only doing three things to them. You can take the first element, which is a value, the rest, that's the tail list, or you can put one together from a value and a tail. A list can be empty, and there's some way of testing whether a list is empty. I can't remember. So over here, when I have a list as 149, first is 1, and the rest is the list consisting of 49. Cons puts them together, so and cons put something in front, just because that's the most efficient thing to do. So you see this in the list function. That's what I really want to look at here. So this function here has two parameters. No, it has one parameter. It's called sum. That's the name. And so you would call it by saying sum and okay, so empty question mark tests whether the list is empty, and in that case we return 0, saying that the empty list has sum 0. Otherwise, we add up the first element and the sum of the rest. That's how you would always loop over lists. You would always do this. You take the head, you take the tail, and you combine them in some way. If you wanted to build lists recursively, use cons. So over here, I'm building the list of squares. Let's see. So if I call squares of 3, what do I get? So I get 9 const with squares of 2. Right? So that's going to be 4 times, followed by cons of 1. That's going to be 1 followed by cons of 0, which is the empty list. So they come out backwards. Yeah?
Is rest and first equal to together?
Yes. Yes, so those of you who know the venerable Lisp, so you may have seen things like car and CDR. So that's the same thing as first and rest. But if you've never seen car and footer, don't worry about it. It's only for historical interest. That's how the operations were called on the original Lisp. And you can pat yourself on the back if you know why. You can look it up. All right, so people often ask me, why is this inefficient? Because when you take the tail, and you take the tail, and you take the tail, and you think, I'm going to have a lot of lists floating around, but of course you don't. The tail is simply a pointer to this list. And so all of the references to the tails, they share the same underlying structure. And that works because there's no way of making a mutation. Since the tail that never changes, there's no worry about sharing it. And that's all. So in Racket, they kind of have this fun way of doing something with circles. It's a little graphical. So I thought that's kind of more interesting than the plain text way. So let's just play a little bit with that. The tutorial is basically very clear, and I just want you to do a little bit with these circles, and in the end you get to do a little mapping.